Let me introduce the next speaker for today. The next speaker is Professor Vijay Shenoy from IISc Bangalore, the Indian Institute of Science. Professor Shenoy has a strong connection with Chennai. He was a BTech undergraduate student at IIT Madras, and he has apparently heard D.K. Pattamal in this venue a long, long time ago. He is a distinguished condensed matter theorist. He works in the physics of condensed matter. He will explain more in his talk. He got his PhD from Brown University in the United States. He's won many awards, including the INSA Medal for Young Scientists in 2002. I think he claims to be young still. He has subsequently won the Shanti Swarup Bhatnagar Award in 2013, the highest prize for science and engineering in India. He will tell us about twisting matter, or let's see, untwisted matter.
Okay, so thank you, Ganesh, for the introduction. So thank you all for coming, first of all, on a Sunday afternoon. And I want to thank you from the bottom of my heart for supporting me, right? Because I'm standing here because of your tax money, right? And all of us scientists are standing here because of you. So thank you very much, and I hope you will continue to support us. Okay. Now, Sandhya said that, there's some interesting problems. Just hold on for a minute. Okay, I'm going to tell you what is really interesting. Okay? All right. So I'm going to tell you a little bit about how there can be a conspiracy between many electrons that's going to change humanity forever. Okay, that's what I'm going to tell you about. And it's sort of put in this untwisting, twisted matter kind of language just to confuse you, right? Okay. Okay, so let me just start by asking you a question. What is it that you cannot live without? Sorry? Phone. Absolutely right. That is absolutely right. And of course, Ganesh, please note down this gentleman's name. He has to be given 2 packets of snacks. Okay? All right. So it is the phone, and we cannot live without this. Right? Certainly my 5-year-old son cannot live without it. Right. Okay. So now, what is behind this amazing technology of phones? Right? It's actually 3 things. The first thing is materials. The second thing is materials. And the third thing is materials. Right? It's materials that make up the phone. Right? So what exactly do I mean by that? It's a material world. Right? Okay. So if you look at the phone and blow it up, don't do that. If you're young, your parents will not be very happy with you. Right? Okay, I think I'm blocking this. Okay. So you see, it has all sorts of materials in it. It has metals, it has semiconductors, it has glass, plastic, lots of things. Right? So what exactly is material? Okay, so there's some light. Okay, I think I should stand here. Okay. So material is matter. And to put in Chennai parlance, matter ke vapa. So that's what I'm doing. Right? So this matter, what we call matter, is something that is continuous, which has some set of properties. This is what I mean by matter, okay? So we see lots of matter around us, like the food we eat, the brick we throw at our neighbor, right? And the petrol we use, and the fresh air that we breathe, right? All of this is matter, right? Okay, so how do we understand this matter, right? What is this matter? How do we understand it? So, the one simple way to see is, you try to classify everything that you see into phases. So what are these phases? So experience teaches us that we can classify matter into 3 phases, right? What are those 3 phases? Solid, liquid, and gas, right? These are the 3 phases. And if you take this mobile phone that you're that is indispensable, you see that it's mostly solid matter, okay? All right, so that's the picture. So now you see, the same substance can exist in different phases. And you know this very well, and when I show this to you, it will be obvious to you. For example, if I take water, it can be in the ice form, which is a solid. It can be in the liquid form, which we drink, water. And it can be in the steam form, that is the gas. And what one can do is one can change the phases by changing the conditions like temperature, pressure, and so on. So you can change phases of the same substance. So what exactly is a phase? So if you think about this, a phase is this collection of something or the other which has some characteristic property. So what exactly do I mean by a solid phase? So a solid phase is a phase which restricts shape change. Now, had the chair that you were sitting in did not restrict shape change, you would fall through, right? It restricts shape change. And every solid, whether it is the sugar cube or whether it is laptop or whether it is point or whatever, they all restrict shape change. So ability to restrict shape change is what makes a solid, okay? All right, similarly fluids don't do this. Fluids have some other properties, I will not get into this. Okay, so the question now, what are the set of questions that have puzzled humanity over many, many millennia, okay? So why are there different substances? That's the first question. Why are there distinct phases? How can the same substance get into different phases, right? And more important and interesting question, which you will see, will come back again and again. What are all possible phases, right? So these are the set of questions that people have been trying to think about for many, many years. Many millennia, thousands of years. So for example, many different civilizations came up with this idea that there are continuous elements, earth, water, fire, and so on. Many different civilizations did this. And then there are other philosophers who said that no, it's not continuous things that make up matter. There are discrete things. And so for example, in India, there was this theory of Paramanu by Kanada and company, and there were things from Greece and so on. So these ideas have been around for a while, okay? So fast forwarding to modern times, if you think about who put forward or when was the clear idea put forward, it was by studying gases. John Dalton made a hypothesis. There are objects called as atoms, right? And if you look at Wikipedia, for example, this is a slide from his paper, and you see he has all these elements that are shown here, and you see he has also said that these atoms can combine to form molecules, and those are the pictures that I'm showing here. Okay, so the matter as we see it is made of atoms, and they can be made of even conglomerates of atoms, which are called molecules. Okay, so if you start from here, how do you understand the phases? How can atoms come together and give you different phases? So this is the question. And that question was actually addressed by van der Waals in a very insightful piece of work in the late 1800s. And what he actually showed was that when a large number of atoms come together and interact with each other, so this interaction could be because of some forces between them, for whatever reason, they talk to each other in some way, and when they come together, you can get different phases depending on what conditions you put these collections of atoms in. Okay, so that was what was shown. So now the question is, what exactly do you mean by a large number? Okay, and what is a large number? So, okay, again, this problem. Okay, the large number is the Avogadro number, so it's 6 times 10 to the 23. Okay, so that's not informative at all. So 10 to the 23 is 1 followed by 23 zeros. Right, that's what is 10 to the 23. So in modern parlance, it's 100 crore. Right? Okay, if you don't know modern parlance, you can go back to ancient India, and it was called a bahula. Right? So if you didn't know this, is a fun fact. Right? Okay. All right. So this is how many atoms are roughly there in this on our scale, on 1 meter scale. Okay. All right. Okay. So now once you have understood this, you will understand the phases as organizations of atoms in certain fashion. For example, in a solid, the atoms are arranged in somewhat nice fashion as I've shown here. In a liquid, the atoms are little less nicely arranged, and in a gas, they're sort of essentially randomly arranged. And because I'm at some finite temperature, I'm at a warmer temperature, these atoms jiggle around. And how do they jiggle around? In a solid, on an average, they not only respect the distances between the other atoms, they also respect the angles. So for example, if this is a 45-degree angle here, it will be 45 on an average more or less all the time. That's what makes it a solid, and that's what gives it the property that it respects shape, because the atoms, their positions respect the angles. Okay? On the other hand, if you take a liquid, the atoms are jiggling around, but they only respect distances, they don't respect angles. Okay? In a gas, they're completely random, they just move haphazard. It's more like Bengaluru traffic, right? Okay. All right, so that's what I've just put up here. Okay. So if you look at solids, many of the solids, as I said, the atoms are arranged in a crystalline fashion. right? So this is an example of a gold crystal, and the gold crystal, the atoms are arranged in this fashion I've shown there. Okay, all right. Now, the same atoms can be arranged in different structures. So for example, this is a famous example, diamond and graphite. Graphite is what you find in your pencil, are carbon atoms arranged differently. In diamond they are arranged in this way, in carbon they are arranged in the other way. So there's no difference between diamond and graphite at the scale of atoms. But let me tell you, the gentlemen in the room, that don't try this, don't try to give a pencil as a gift. It doesn't work, okay? All right, okay, now I want to show you something else. Take a look at this thing. What is this? This is actually a wire which is used to transmit electricity. If you look at this wire, it's all solid, yes? However, this piece here, which is metallic, copper, is a conductor of electricity. Whereas this little chunk of plastic, the sheath of that is electrically insulating. So now suddenly you realize that, hey, just being solid is not enough. There seems to be distinctions in the solid phase itself. There are conductors and there are insulators. You get the picture? The solid itself can be a conductor or an insulator. Hey, what's going on here? So this is a little strange, right? If you look at diamond, diamond is an insulator and graphite is a conductor. You see, they all started with the same carbon atoms. Okay, so this is the fascinating thing about this. Why are there insulators and conductors? Okay, before I pose that question in a sharp way, I want to tell you that conductors played a great role in the Industrial Revolution, and electricity started, had to be transmitted and so on. So metals were studied by lots of scientists in the 1800s. And around 1850, there was a beautiful discovery that was made. I have some technical terms here, just ignore them. There is one property of the metal, there is another property of the metal, divided by temperature. That number turns out to be independent of which metal you are studying. What does that mean? That means being a conductor has a characteristic property, which is this number, universal number, independent of which metal you are talking about. What does that mean? That means that there's something common in all metals, just like there was something common in all solids having shape, resistance to shape change. Okay? So this leads to a question. The question is, why are there insulators and conductors? Why do they have some common characteristic? More interestingly, are they a phase? If they are a phase of what? Remember, the solid was a phase of atoms. What is the insulator and conductor phase of? Okay, so this is the question. And this question puzzled the scientists for a long time, until somebody made the important discovery, which is the discovery of the electron. Right? The electron was discovered in late 1800s by Thomson, and this is a particle which is very light. How light? It is 1,000 times lighter, typically, of a typical atom. And what is its weight? Well, 29 zeros and a 1. Right? That many kilograms. So if you want to, if you buy 1 kilogram of any material, it has roughly 10 power, 30, if it were weighing in electrons, it will have 10 power 30 electrons. Okay? All right. Okay. So now the electron was discovered. Very soon, that discovery led to the discovery of the atom, the structure of the atom itself. And Rutherford, based on several set of experiments, concluded that the atom has the following structure. It has a central nucleus and the electrons that hover around the nucleus. The nuclear size itself is 10 to the minus 15 meters, right? So the nucleus is very, very tiny, and the electrons are hovering around, and the average distance on which they are hovering around, if you look at that, the size of the atom becomes 10 to the minus 10 meters. That means, if you want to stack atoms one by one by one by one by one, starting from the floor to my height, you need about 10 billion atoms, one by one by one by one, to come to my height. That many atoms have to be stacked together to get my height. That's the size of an atom. Okay? All right, good. Now I'm ready to answer, where do insulators and conductors come from? Okay, so just about that time, that once the electron was discovered, people started working on lots of ideas, and one of the central ideas taken in this area is by Drude, who made the following step forward. So what he said, that let's think of an atom. An atom comes in, gives an electron, and it becomes an ion, which means it becomes a positively charged object because the electron was negatively charged. And so the ions arrange themselves in this fashion, and then you see the electrons are moving around in this background of ions. Okay? And he made this postulate that the electrons by themselves form a gas. So imagine what a solid is now. A metal would be the ions sitting in place, like what I've shown there, and the electrons whizzing around and forming a gas. This was the picture that he had. Okay? All right. From there, by some mathematics and analysis, he showed where the Wiedemann-Franz law came about. Remember, what was the Wiedemann-Franz law? That there is a universal parameter associated with all metals. So he was able to explain this. Great success. Remember, Wiedemann-Franz law was 1850. This was 1900. A 50-year-old puzzle solved by theory. Okay, fantastic advance forward. Okay, so the key conceptual advance was the following. A typical matter or material is a conspiracy of 10 power 23 electrons. That's the main message. So what happens? The atoms come together, some of the atoms give out electrons, there's an ionic background that forms, and the electrons themselves organize into different phases in this ionic background. That is what a material is. Okay? So this is the main idea. Okay? Now, Drude solved a 50-year-old puzzle, right? Okay, let's see whether he did or not. So Wiedemann-Franz law was 50 years old and he solved it, he explained it. And if you use the physics of that time, what people believed was the physics of that time, which is Newtonian physics, a particular quantity called specific heat, never mind what it is, will turn out to be 9 by 2 from theoretical considerations. You can go and measure this quantity in the laboratory and it turns out to be 3. Okay? There is a small problem. What is it? The problem is that 9 by 2 is not equal to 3 for usual values of 9, 2 and 3. Right? So this is a problem. So if the theory is successful, it is wrong. What? Okay, that's the problem. You see? So there is a puzzle. But there is a conceptual advance made that there is a picture that a material is a phase of electrons. So what do we need to do to repair this now? Okay, so the resolution required an entire revolution in physics. And that revolution is quantum mechanics. Okay? And you will see that I have to introduce some quantum mechanics. Right? Maybe I'm being ambitious here, but Sandhya has already done the job because this is all going to be about traffic rules. Okay, and I'm going to show you what are the traffic rules in the quantum world. Okay, so let's see what happens. So before I discuss quantum mechanics, I just need to refresh your memory about what Newton had talked about, and many of you have written many 5-mark questions on this, right? Right? Okay, so a moving particle, so if I run, for example, you say I have momentum, mass times velocity. Okay? And if I have a certain momentum, I have some energy associated with motion, and this is what we call as kinetic energy. So if I have a classical particle, if I look at the momentum will determine the kinetic energy by this curve. So if this is the value of momentum, I read off this graph and that's the energy. Okay? In classical physics, a particle can have any momentum. So if the momentum is on this side, it's moving to the right. If the momentum is negative, it's moving to the left, and it can have any value right or left. Okay? All right. Now what I'm going to do for you is I'm going to tell you I'm going to give you quantum mechanics in small quanta. So that's what I'm going to do. I'm going to think of this phase of electrons in the following way. I'm going to construct for you a one-dimensional chain of ions. The pink guys are ions. They're just sitting there. And the electrons are moving, the small blue guys, they're moving around in the background of these ions. Right? Okay. So what are the rules they're going to follow? That's what we're going to see. So it imposes certain traffic rules. What are the first traffic rules? There are, how many traffic rules are there? There are 4 of them. Okay, so the first rule is the following. An electron in quantum physics cannot have any momentum. There is a quantum speed limit or quantum momentum limit, right? So it can either move to the right by some value called pi. Okay, don't worry why that is pi, it can be made anything you want, right? Or it can move to the right by pi. Second thing is, your momentum cannot have any value between minus pi and pi. It takes only discrete values. So those are the little dots that I put here. So if I think of this as momentum axis, these little dots are the allowed values of momentum. Don't worry where these rules come from. We know they are correct. That's all you need to take for now. Okay? So there is a speed, there is a momentum limit and momentum of discrete. Okay. How many such momenta are there? There will be as many momenta as the number of ions you put in the crystal. Okay, good. So this is rule number 1. Rule number 2. You see, just quickly remind you, in classical physics, you can have only one energy for a given momentum. In quantum physics, what happens is if you give me a momentum, it can have different energies. So for example, if at this momentum, it can have either this energy or that energy. And the combination of the momentum value and the energy together is what we call as a quantum state. Okay? So what I've done here is I've put 2 rows of dots here. So this row of dot corresponds to this energy and that row of dot corresponds to the other energy. And this is what we call as bands. Okay? So this is called the lower band and that's called the upper band. Now if you see, if I had a particle sitting in this state, if it wants to go to that state, the energy change will be from here to here, which is very small. On the other hand, if I want to go from one band to the other, so suppose I want to go from here to there, then I have to change the energy from here to here, which is a very large value. So if you jump in the band, it costs you very little energy, but if you jump across the band, it costs you a lot of energy. Okay? So that's what happens. Okay, quantum rule 3. So this is the real quantumness of everything I'm saying. It's a little hard to imagine. Every quantum state has some sort of phase angle associated with it. Okay? Don't worry where all this comes from, just take it from me, right? It's a phase angle. So how do you think of this phase angle? You can think that there is some kind of dial on the state, and that dial can point in any which direction it wants. Okay? So this is called the phase angle. So what is the gist of rule 1, 2 and 3? 1, 2 and 3 is that every quantum state or a pigeonhole, you see I drew little boxes. This is a pigeonhole. It is characterized by momentum, energy and some kind of angle. Okay? Alright. Now, I have been talking about a single particle. Right? But you remember I need to put 10 power 23 electrons into this. So I have to start talking about what happens if there are many particles. Now here is something else that we discovered over many years. Right? Quantum particles come in 2 varieties. The first one are called fermions. If I have 2 fermionic particles, they cannot occupy the same quantum state, just like you. If you are sitting in a chair, nobody else can come and occupy it, of course, unless for other reasons, right? So that is exactly what these guys do, right? Okay. And there is another class of particles which I will not talk about at all in the rest of my talk. These are bosons. If you have bosonic particles, any number of particles can occupy the same quantum state. Okay. All right. So now you see I've told you about pigeonholes. Why not think about pigeons? We see them every day, right? At least in Bangalore we see them. I don't know whether you see them in Chennai. Okay. All right. So pigeon is an electron and a pigeonhole is a quantum state. How do you understand this fermion business? So you see, if I had pigeons sitting in all these holes, if a new pigeon comes in, it doesn't have place to sit. Right? Very simple. Okay? So now we have all that is needed to understand phases of electrons. Okay. So how do we understand a metallic phase? The first point is that there is a condition under which you will get a metal. What is the condition? The condition is that there are not enough pigeons to fill the lower band of pigeonholes. That's the condition. Okay? So you see I start with empty sets of pigeonholes and I start placing pigeons in them. Okay? So these pigeons have gone and sat there. Now this is a metal. Why? Because suppose there's some smell of food there. So what happens? This pigeon starts jumping there. It can because it's empty. So there you go. It jumps. Okay, I have to make this fellow happy. Okay, it jumps and you see it can move. So this is how conduction takes place. When you apply voltage, you see current starts flowing. It's in exactly this fashion. So the pigeons can jump, 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 and that's what gives you the current. Got the picture? Yeah. Okay? What happens if I have insulator? Now consider a case where you have exactly the same number of pigeons as the number of holes in the lower band. Then what happens? You will get a situation like this. This entire band is filled. Now if a pigeon wants to move, what can it do? It can only jump to the upper band, right? But hey, I told you to jump to the upper band, it costs a lot of energy, right? So unless you have a lot of energy, you cannot promote a pigeon to the upper band, which means if you apply a small voltage, you will not have any current flow. For example, if you see lightning strike, what has happened? The air was insulating, but there was so much voltage created between the clouds that it had enough energy to run through. You got the point, right? That's called breakdown. So for small voltages, you will see that it is an insulator. Okay? So this is how you get the insulating phase. I think I ran through many things. Now, why are these phases important? Now, if you look at, I use the word semiconductor, I'll tell you, the semiconductor that we know, like silicon, for example, the one that I'm showing here, is actually an insulator. It becomes useful in building the transistor, which has allowed you to have your mobile phone, by doping, by creating quantum states which are accessible at low energy, by a process called as doping, by intentionally putting in impurities. Okay, that's what this thing is. Okay, I have to tell you about one more phase of electrons, which is actually extremely interesting phase. So I didn't tell you one little thing, I suppressed this. Each electron is a tiny magnet, right? So you can imagine that each electron is holding a bar magnet where this up arrow is like the north pole. So you can have a phase of electrons where all the electrons in the lower band, their north poles align together. And when their north poles all align together, you get a magnet. Okay? So I have now showed you 3 phases of electrons. What are they? Right? It's a 3-mark question, so you have to give 3 points, of course. Right? So it's the metal, the insulator, and the magnet. Okay? So this is the message. Now I want to impress upon you what is the importance of this. Okay? The importance of this is the following. These 3 phases are behind the world that we have today. What is the thing that runs our world today? It's computers. Think of any human activity, any, banking, transportation, anything, it's computers, right? So the mobile phone and the computer is entirely supported by these 3 phases of electrons: magnets, insulators, and metals. So you can see that this picture is not an exaggeration. The whole world sits on these 3 electronic phases. So you can see how important this is for humanity. Okay? So now it seems that I should stop my talk here because I've told you what is important. But wait, there is an obvious question, right? And the obvious question is, are there other electronic phases? Why is this important? Who knows? We may have to go and live in Mars, right? So we may need phases which will support our existence on Mars, for example, right? Okay, the answer to this question is yes, there are other phases. So what are the other phases? Okay, so the phase was actually discovered in 1911. So that phase is when you cool a metal at a particular temperature, in this case of mercury, it is at minus 270 degrees centigrade. Don't bother about taking your sweater to that temperature. It doesn't matter whether you have a sweater or not. Okay, it's minus 270 centigrade. Okay, and this material has actually, many technological applications. So for example, if any of you have visited an MRI machine for medical purposes, that actually runs on this superconducting idea. The Japanese have already created these so-called magnetic levitation trains. I've shown you levitation here, right? And those trains run at 600 kilometers an hour, right? Which is slightly bigger than the Shatabdi, which is 70 kilometers an hour, right? Okay, right? So this is a truly quantum phase of electrons, and the highest temperature practically achieved for this to exist is minus 100 degrees centigrade, which means that this technology is definitely for special purposes like maglev and MRI and so on, but cannot be used in your cell phones and all, right? You cannot do, we cannot have a technology that runs at minus 100 degrees. Okay, now I'm coming to the topic of the title of my talk, Twisted Electronic Phases. And let me tell you, friends, that, condensed matter physicists, the people of my area, they think that theorists are a necessary evil, right? So I want to tell you that this is a phase that was predicted by theorists. Okay, not me, but okay, I'm just giving the pat on the back is for all theorists, right? Okay, right, it was by 2005, 2010 it was predicted. And what happens here is, remember I told you that each state has an angle, some phase angle associated with it. So what I can do is I can tilt the pigeon according to this phase angle, right? And now this is an insulating phase where the pigeon tilts as you fill it. So you start with one pigeon, the next pigeon tilts, and you see that there is a twist that is put into this pigeon, you see. So this is what is the twisted insulator. This is the twisted electronic phase that I was telling about. And friends, this was discovered 10 years back, right? This in physics is a big deal because 10 years is a long time, short time, right? Okay, all right. So this has very strange properties. So these materials are, if I take a material and cut a surface, so imagine that this is the surface and the rest of the block is the bulk of the material. So what you will be able to theoretically show and also experimentally verified, and that's this picture, never mind what it says, right? The surface of this material will be metallic. It is guaranteed by laws of physics to be a metal. The surface alone is a metal, the bulk is insulating. Okay? There are spectacular applications for this. So I have a challenge for our friends in the audience, right? Can you think of ways of using this? Don't worry about what the theory says. Can you think of some applications using such a material? You don't need to be a physicist to do that, right? Okay. So the importance of this field, the people who built these ideas from which this twisted electronic phase was actually discovered were given the Nobel Prize in 2016. Okay. Now, okay, so one way to think about it, so the Nobel Prize is already given, so why should I work in this area? Right? Because I'm not going to get Nobel Prize again. That's not the right thing to ask, because if you ignore this, you're going to lose big time, and I'm going to argue that. Right? Okay. So I'm going to tell you a little bit about some exciting thing that's happening in the world, and that's called as quantum computing. So this computer is what is currently called as classical computer. What exactly is classical computer? All information in that computer is stored either as zeros or ones. And all processing of information takes place by, twirling around zeros and ones. Okay, that's what happens. If you have a quantum system, what actually happens is you have something called as qubits, in which you can actually encode all possible combinations of 0 and 1. And you can process the full thing, right? And what that does is some magic. Okay, I'll just start by saying that this is a game changer. How is it a game changer? I just discussed that all of banking, etc., is based on classical computers. So just think about this. You get into the computer, you give you a password. Okay, I have some connection, right? Okay, all right, okay. So what you can do, for example, is I can go and put in, some wires on your telephone line, and I can see what password you are sending, right? So then how can you be safe with the password? So the secret to this is that password is not sent as the password you type, right? It is sent as something called encrypted. It's put into a secret key and then sent. And the sender and receiver have the key to undo this. Now that key is based on the fact that these classical computers, they multiply fast, but they cannot factor into things very fast. It's based on that. It's based on the fact that something is very hard for the classical computer. But it's not so for the quantum computer. So if I have a 150 qubit quantum computer now, just for a moment think about this, the world will change instantly. We will go to barter system because the banking system will collapse, because I will read all your passwords and I'll transfer all the money to myself. You get the picture? It's all okay. Without the class. Okay, that's a different problem. Okay. All right. Okay. All right. So this is a game changer. Okay. So it's going to change the way we live. Okay. So the key challenge is how to build a quantum computer under ambient conditions. This is a technology challenge. And we know the concept. We know that, I have not discussed how this happens in this talk. We know that these twisted insulators and superconductors can actually help you build a quantum computer. What does that mean? The key physics question is how to make superconductors and twisted insulators at ambient conditions. This is the central question. And this is the question that I'm trying to, people like me and other theorists and experimentalists are trying to work on. And don't bother about reading the details. So we have done some work and shown that what are some class of materials that we can do. So this is the only transparency which is like a report card from my side. Okay? All right. Okay, there are key intellectual challenges. Okay, and lots of very, very sharp scientists are working on this. Can we classify all phases of matter? Okay, this is a very interesting question. It has connections to all sorts of beautiful mathematics and other areas of science. And I want to sort of conclude by telling you about connections to other fields. So you may think that, oh, what this guy is telling is about just matter and things like that, you know, some cell phone and all. Who cares? I'm worried about the structure of the universe. Right? Good. So I'm just telling you that if you take a neutron star, find the nearest neutron star. It's just, I don't know, 1 billion light years away or something. I don't know. It doesn't matter. You can get there. Right? Very far away. Right? All the phases that I discussed are realized inside a star. So if you study this area of physics, you have something to say about another area of physics. So more is different. What does that mean? When many electrons come together, they produce things that no single electron could do. It's a bit like human beings. Right? And in fact, Sandhya's problem, what she was talking about, can be cast in this language. There are all these neurons. When these neurons come together, they produce the brain. How do you think about this process of many things coming together and producing new stuff to understand the structure and function of the brain? Okay? So that's one problem. Okay. So let me just give you my final word. This is the most important slide. Please look at this very carefully. Every epoch of humanity's progress was governed by a particular phase of electrons. So when you look at the Stone Age, that was the insulating phase of electrons that governed that epoch of humanity's existence. When you went to metals, that was the quantum liquid phase of electrons, the metallic phase. And the last so many years, say 20, 30 years, was governed by semiconductors. So what is the goal now? The goal is to tell you, or if I can get this, is that the superconducting and twisted phases are going to lead us to the AI age, the artificial intelligence age with quantum computers. Right? So the next epoch will be unleashed by untwisting twisted matter. I'm sorry, Sandhya, there are more interesting things to do. So all of you, young people, old people, doesn't matter, age is not a problem. Just come to Bangalore and start a conversation with us. That's what you should do. There's nothing else worth doing. Thank you.
Okay, thank you very much for that very nice talk. Before everybody catches the next train to Bangalore, we will ask you some questions. We did get a few questions, so please do keep sending us your questions. So here's a question received from the phone number ending in 4695. What does a phase rigorously mean? How can one define a phase?
Okay, whoever asked the question asked for it. It's the fixed point of a renormalization group flow with no relevant operators. Is that rigorous enough?
If you have booked your tickets already, you can cancel them now if you like.
So, all right. So we know the rigorous definition of phase. And if the person who asked this question is a physicist, they can of course ask me at the tea time. But broadly speaking, you know, so I can give you a biological example, right? So for example, if you biological analogy, I should say, right? So if you take living matter or living things, you can classify them into plants and animals. Right? So in some sense, that's the largest phase-like classification of biological objects. Okay? And if you take animals, you can classify them as vertebrates, invertebrates. So you see, all vertebrates have some same character. All invertebrates have some other character. So when we physicists say that there is a phase, some set of objects come together. If they, for example, have a generalized resistance to shape change, you would call it solid phase. Right? There are very, very precise mathematical ways of characterizing this, the rigorous part of the question. I don't think this may be the best place to put those things forward, but okay, yeah. But I hope I gave you the idea.
Okay, let's move on to the next question. Maybe two related questions. one from a phone number ending in 3809 by SMS. How relevant is atomic theory in this age of quantum physics?
Atomic theory is...
So maybe I'll ask the next question too.
Yeah.
So this is a question from Satya Prakash. We know that atoms don't follow the laws of classical physics. Then why do we use classical physics for some properties?
Okay, all right. So the first part of the question, okay? So Feynman posed this following, everybody I hope knows Feynman. If you do not know Feynman, first of all, my condolences to you. Second, you please go and do Wikipedia immediately. Don't, you can switch on your cell phone. Do what you want, but get to know who Feynman is. Okay, all right? So Feynman had a fantastic way of posing this point about how important atoms are. He asked, suppose the Earth were to go extinct now, right? And you want to send 20 words by a rocket to some other world, and somebody will capture that information, they can start from there. What would you send them? So Feynman said, one line, just write that matter is made of atoms. Then if that civilization is smart enough, they'll figure out everything else. Okay? So that's the first part of the question. No, there's no need to clap. You're clapping for Feynman, not me. Okay? The second question, when are quantum effects important, right? So for example, there was cargo, Sandhya's cargo. So why didn't Gautam use quantum physics to do that? The reason for that is, this cargo is made of probably 1 million atoms or so. Is that correct, Sandhya, roughly? So it's pretty heavy. So when things start getting heavy, so you may think that I'm fluctuating around like a nut, but that's not because I'm quantum, that's because I'm a nut. Okay, so the point is, what happens is when you get very light, these quantum effects become important. So the question is, what is the object that you're studying? Is it very light? So you have to understand what very light means. And for this, you have to know a quantity called as Planck's constant, which governs the quantum effects. So when things are very light, and they are sort of they start becoming compared to something determined by the Planck's constant, then you will see that you have to take quantum effects into account. And any electronic property, if you want to study it seriously, you have to take quantum effects. So for example, I'm showing you this pen here, it has a metallic clip on it. This clip, if you want to understand why it shines and all of that, you have to use quantum mechanics. This metal cannot exist if you try to, in this way, it cannot exist if you want to describe it within classical physics.
So there are still some properties you can understand using classical physics alone?
Absolutely. But like for example, cargo transport.
So one more question, from the phone number ending in 8020. You discuss phases in systems with 10 to the power 23 electrons. Are there well-defined phases in systems with just a few electrons?
That's a fantastic question. Okay, so from a theorist perspective, if I have a few number of electrons, it's strictly not correct to describe a phase. But however, if you take sufficiently large number of electrons, right, you could start seeing the properties of certain phases. So for example, you actually have systems which are what are called as nanoparticles. So what I showed you that a bulk gold will have 10 power 23 electrons. But you can create nanoparticles of gold which are used in cancer therapy, etc., which are very important for technology and so on. So if you take those, they will have much fewer electrons. But you see, they still show metallic character like what I showed you, right? They have slightly different metallic character. We also understand how to explain that slightly different thing. So the answer to that question is, roughly yes. If it is too small, you cannot describe it as a phase. But if it is some intermediate number, like maybe 10 million, 100 million or something, you can still think of it using phases.
Maybe we'll take one last question before the break.
Yeah.
Here's a question from the phone number ending in 0748. How does water exist in all three phases of matter at the same temperature? Maybe you could expand on this a little bit. What determines which phase a system is in?
Okay.
Oh, so carbon, for instance. Why is it graphite or why is it diamond?
Okay. All right. Okay. So I'll give a slightly long answer to this. So why are there different phases, and why are there what causes phase changes, and how can phases coexist and all that? Okay. First point. Nature, if you let it be, if you take a bunch of atoms and if no other considerations were there, the atoms will move around in such a way that the total energy of the system, the total energy, is minimized. This is something that we all know very well. Left to ourselves, we'll all be asleep, right? So precisely that idea. Nature also follows the same laws, right? However, there is something called as temperature. You see, we get hot, the things get hot. What that means is that there is some kind of random jiggling of these objects that happens. So if the jiggling energy becomes larger than the energy that's keeping these things together, then there is a phase change and it goes to another phase. Because it's better for it to be in this jiggling state than to be in the state where everything is ordered. Okay, this is why there are phases and phase changes. Why are there different phases? Like in the water phase diagram, if I am assuming that the person knows the water phase diagram, there is a point where all three phases coexist. That is a place where the give and take of all these three phases is exactly the same. So they coexist. Okay? And what was the second part of the question?
What determines which phase?
Okay, all right. Okay, so for example, this is a very interesting question. So why is diamond expensive and why is a pencil cheap? Okay, rarity is a very nice answer. Okay, that's a practical answer. Okay, but now I know chemistry, I know all this stuff. So what I can do, I can take graphite and do something to it at home and convert it to diamonds. In fact, now there are whole industries which are actually producing synthetic diamond. Right? Okay, you want to start one? Okay, all right. So this is the point, okay? So the fact of the matter is the following, okay? So I told you that different phases have different energies. So what actually happens is, if I want to take graphite and convert it to diamond, I have to rearrange the atoms, right? In graphite they were like layered and then diamond they were in some different structure. When I want to rearrange that, although this state is lower energy and that state is higher energy, I have to climb a hill up and to come down to this lower energy. And that hill is very high. For example, if you want to start from carbon atoms and make diamond, you have to have very high temperature and high pressures, etc., to actually climb that hill and come down. That process is expensive. Because I have to, buy power and so on. At least if I'm in certain parts of India, I have to pay the bill. Yeah.
Thank you very much for the very nice, energetic talk. Thank you so much, Vijay.